Okay, good morning. So before, I think today we're going to discuss the relational data model. Before we start the discussion, I think some of you asked me about the Oracle Apex. So if you remember that in the when we discuss about the syllabus, I actually can show you the kind of a so that for this class, we are going to use Oracle Apex for all the programming needs and assignment, okay? And then you have to go to this website to request a free account. So once you have a free account, then we can pretty much, you can upload the scripts or you can practice SQL programming with that free account. Okay, so the first thing you have to go to this website for to register for a free account. So once you finish registration, yeah, I think, and then you suppose be able to come to like this kind of a interface, so sign in page. So for me, I think my past my database. So this kind of a table space. So I think in registration process, it asks you for the table space. You can assign, give any name you want. But I think pretty much maybe it should be unique. So I show I select my table space tag, NXW and DB. Then the password, then let's do the sign in. Okay, so once you finish signing, so you can come to this kind of interface, okay? For this interface, I think we mainly use the SQL workshop. This is the only thing we're going to use, okay? So you click this SQL workshop, okay? Then according to the, lost something here. According to the syllabus, you need to download, sorry, I think I probably have to log in again. So you need to download a script file. So this script file here is basically used to set up a database that we can use for our SQL programming study and also for the assignment, okay? So you just simply click this link, then you download this file. So since I have just downloaded, then the next step, we're going to upload this file, script file for execution. So then you have to click this SQL script. Okay, so right now we enter the SQL workshop. Then you click this SQL scripts, then it will allow you to upload. So if you look at the menu bar here, we have delete, checked, upload, quick SQL will create. So you just click this upload, okay? Then we're going to browse to find the file. So I'm going to click this choose file button. Then I think this is the file I just downloaded. So that's the file you need to upload called company db underscore new dot SQL. Okay, then you do the open. Okay, then I think the script file you probably can skip here. Then you just do the upload. Okay. So once the upload is done, this script file will be showing here. Okay. Then you just click on the right. There is a button. You just click this run. It will run the script. So then before you run the script, it asks you for the confirmation. So you just click run now. Okay, so this kind of some kind of a result. So those are the feedback. So the first one, it does have arrows. It's showing that a table or view does not exist because the first line of the code will be drop table department cascade constraint. Since we haven't created any table yet, so that's why this command will create some, will cause some error, but this error is not called kind of fatal error. So that's what means that just give you a warning, then the remaining statements in this script file will be executed. So then you have table created, then you have rows inserted. Then when we try to drop another table, then you got the similar error, but that's fine. then you create table, then table created. So that's pretty much what you're going to see. So when this basically, I think you're supposed to have the same error information and the same statement executed here. So I think after that, basically means that you have created the table already. So how do you know if the table created? There are several ways you can do that. And one way that you go to the SQL workshop, you can either go to the object browser, but here it is automatically showing here that this is the tables that are created. Now, this kind of the time, 76 seconds ago, okay? You can click the table, then it shows, in this case, this part just we're going to discuss called table schema. So it shows the column name along with data type for each column, and some kind of null value means that the constraint, whether that attribute can take null value or not. And also it indicates primary key, so means that this field is primary key. So this simply just shows the table structure. But if you want to see the content of the department, you just click this data. Then it shows. Okay, so means that in this department table, there are only 3 records. So this is more like table. The first line indicates the column header, and then from the second line all the way to the last line just shows each individual record. Okay, so this basically, I think, if you're curious that about this part, then I think you can go ahead to register for the Apex account and then run this script file. So once we have successfully executed this script file, then basically means that we have table created already. So we have a small database that we can practice with SQL query. So another one that you can also go to the SQL commands. So you just do the select star from cat. Cat means catalog, okay? Now if you run this one, it just simply shows the tables under your table space. So right now you have 6 tables, okay? So then you can do the similar thing. So for example, select star from, for example, department. So in the Oracle SQL, the table name, attributes name, they are not case sensitive, okay? So that's why you use capital D department or our uppercase department or our lowercase department. They're going to treat it as the same thing. So department. So if I highlight this command, I do the run, then it simply just shows list the records in that table. Okay. So I think at this moment it's fine because we haven't started SQL programming yet. So I will remind you maybe before we start SQL programming to make sure that you have your account ready, your database created. Okay. So that's pretty much about the how to use Apex and how to upload the script file and run it, and also how to examine if the table has been created. Okay, so so can you try the game? So let me show you. So I think for this class, yeah, this is the. So if I click, I think I just tested this morning. If I click, you see it's automatically showing the download here. So I think why not you try now? I think now it should be working. Okay, if it's still not working, let me know. Okay, so at least at my. Oh, you just did it? Huh. Okay. Okay, then that's fine. So let me, I think, let me send an email to the whole class. First, do the announcement. I think hopefully I can. Thanks for letting me know. So, do I? Yeah. Okay, so let me, yeah, let me go to the contents. I'm sorry, it's not doing that. So then let me send email to the all the. I think it's probably easier for me to just send email. So I think we have how many sessions here? Okay. So I just sent email because I want to make sure. Because I think I have at least one student had that problem, so let me just make sure. Okay, I sent this files through the email. Okay, so if you cannot download it directly from the Blackboard, then just use the file I just sent you. Okay, that's pretty much about the Apex. So then let's go back to work about, okay, the relational data model. Not sure if let me shrink this one to make it smaller. I'm able to see it. Okay, good. So I think relational data model is kind of one of the key chapters we're going to cover in this class, okay? Because once we go to the SQL programming and the PL/SQL programming, they all based on the concept of the relational data model. So what is a relational data model? So in this class, we're going to discuss what is a relational data model, as well as relational data model constraints. Then we're also going to discuss the database update operations. Those operations might have potentials to violate the relational database constraints. So how we're going to handle that. Then finally, we're going to discuss functional dependencies and the normal form, okay? So regarding to the relational data model, it is actually based on the concept of a mathematical relation. So the relational data model was first proposed by Dr. Ted Coates from IBM in 1970 in a seminal paper. And this paper called Relational Model for Large Shared Databanks is published in the Communications of the ACM in the June edition. So this model, once this paper has been published, it received a wide attention or interest because of the simplicity of the model and also because it has a math foundation. So basically, this model uses the relation, a mathematical relation as a building block. So in the mathematical term, a relation is somewhat like a table. Okay, so a relation is table. And also it has its own theoretical foundations in the set, also set theory, that's in the math term, and also the first order predicate logic. So those kind of pretty much the foundation theoretical foundation for this model. And once this paper has been proposed, I think there's several research prototype of the relational database have been kind of developed. And then in the early 1980s, the first commercial implementation made available on the market. So those are the Oracle relational database system called Oracle RDMS. And also there's another one from IBM. It's called SQL/DS system. And nowadays we have kind of large number of different relational database systems. For the commercial system, we have Oracle database. We have Microsoft SQL Server, right? We also have DB2 from IBM, and also I think Informix from IBM. Then there are also some kind of open source database systems such as MySQL database and the Postgres database. And also relational database have been widely used in the industry to support the organization's daily operation and also to support their decision-making process, okay? So according to the informal definition, we can represent a database as a collection of tables, okay? And each row in the table represents a fact that typically represent a real-world entity like a computer, a student, a classroom, a class, or can be a relationship like kind of like a script in the at EULAR or in the WORDS database. We have like a transcript, okay? So transcript basically relates each student with the courses they have taken along with their grades. And also the table name and the column names interpret the meaning of the values in each row. So if we have a very good easy understanding table name and column names, it's very easy for the user to understand what's the kind of data stored in the database. So those are the informal definition of the relational data model. So this slide shows the example of a sample database. So in this case, this database contains at least 3 tables, okay? Each table has a name, like this one, the first one, the employee, the table name. And also each table has a column headers. First row are referring to the column header, right? So if the column header gave you very easy to understanding name, then we pretty much know that each individual element in this table, what does that mean? What does that represent, right? And also we have kind of this notation I think we discussed in the last class. So in the employee table, we have SSN, stands for Social Security number, underlined. That indicates SSN is the primary key of this table. By primary key, it means that every record in this employee table will have a unique SSN value, okay? So in this case, because of this primary key, so primary key is also a constraint of relational tables. So because of the primary key, then each relation table does not have any duplicate records. Okay, so every record will have a distinct primary key value. Then every record should be distinguishable from the rest of ones. Okay. Okay, so then for the formal definition, so the table is called a relation. Okay, then the row in the table is called tuple. Okay, the column header is called attribute. Okay, and also the data type describing the types of each attribute is called a domain. So in the relational data model, each attribute will have to supply the domain so that we're able to validate if a value really satisfies the domain requirements. So for example, in this case, SSN, the domain should be 9-digit number, right? So then we can easily validate if every SSN is valid. So if we happen to see an SSN is not a 9-digit number, maybe 8 or maybe 10, then we know that that SSN is not valid. Okay, so that's why the domain usually help us to evaluate whether an attribute value is valid or not. Because in the database, we really care for the quality of the data. I think some of you from information quality, some of you from information science program, but regardless which program you are with, then if you need to use data in the database, you have to make sure that the data is of high quality. Why? If the data is inaccurate, it's missing, then are you able to trust what you get from database? No. So that's why database is not used just simply as a storage of the data. It's mainly used for supporting all kinds of the operations in the organization. Okay, so that's why the data must be of high quality, so that user has confidence in the data, so they can trust whatever patterns or information is retrieved from the database. Okay, so that's why the domain constraint is very important to help to ensure that every item in the database actually has a valid value. Okay, so but in this in this class, we're going to use the table versus relation, tuple, record, or row. I mean interchangeably. So and attributes. I think usually I use attributes, but we kind of mix the definition of the informal and formal, basically in the discussion. So this shows the formal names for the column header, the attributes, the relation name, and the tuples. Okay, and I think in this case we forgot to underline the SSN. That's supposed to be the primary key. So every relation table must have a primary key. So that's kind of a requirement of this relational data model. Then the domains. So each attribute has a domain. So a domain is given a name, a data type, and the format of that attribute. Okay, and also domain can specify all possible valid values an attribute can take. Okay, so that we're able to do the validation. So here shows some examples of domains. For example, for the USA phone number, it should be the set of 10-digit phone numbers that are valid in the US. Okay, so we can easily kind of identify several invalid phone numbers, like phone numbers with all 0, right? Maybe phone numbers with all 1, all 9. I think that's not usually that's not the numbers that will be used in reality. Then for the SSN, that will be a set of 9-digit numbers. And for the names, the person's name should be the set of character strings that represent the names of persons, but sometimes we also have state name, product name, and the class name, and that's fine as long as the name that makes sense and also satisfy the data format and the data type definition of that attribute. Questions? Okay, so then the relation schema. So a relation schema simply just represents the structure of a relation or a table. Okay, so that's why in the relation schema, it only need to show the table name or relation name along with the attributes included in that relation. Okay, so the kind of relation name can be denoted as R parentheses A1, A2 all the way to the AN. So R is the relation name, and A1, A2, and AN, each of them represent an attribute. So here I give you one example. So we have customer relation. Okay, so this is the customer relation schema. So we have customer name, so the relation name customer, then we simply list all attributes in that parentheses and separated by comma, and then the primary key is underlined. Okay, so that's kind of the typical representation of a relation schema. Okay, then each attribute usually need to have a domain so that you know exactly the data type and format that attribute can take, and also the possible valid values that attribute can take. Then we also have kind of that definition of the degree of a relation. So degree of a relation simply represents the number of attributes in that relation. Okay, so for example, this customer, it has 4 attributes. That means the degree of customer is 4. Okay, so if you come here, like the student, how many attributes we have here? The 7. So the degree of student is 7. Okay, questions? Then we're going to have a formal definition of relation. So that's according to the relational data model concept. So a relation actually is formed over the Cartesian product of the set. So then I'm asking, what is a set? So set is a mathematical term. So set basically is a collection of distinct elements or objects. So that means that, I think if you know the programming, that means that a set cannot have duplicate elements. So each element in a set must be distinct. So that's a requirement of the set. But if you have a list, if you have a bag, then that's not needed. So a list, a bag, an array can have duplicate elements, right? But a set cannot. Okay, so here give you one example, like A stands for a set. It contains 4 distinct elements. D is also a set, contains 3 distinct elements representing colors. And then X can be also considered as a set. So then each element considered as a composite, right? So compared to the X to A or D, we compare that each element contains multiple fields or subcomponents. Okay, so this basically means that X is a set with 2 elements, and each element, in this case, we can guess representing with 3 fields, first name, last name, maybe the age, how about that, okay? But anyway, you have to make sure that the set must have a unique element, okay? Then the Cartesian product of 2 sets, A and B, is defined to be a set of all ordered pairs. So we represent the pair as small a and b. So small a is an element of set A, capital A, and the small b coming from the set B, okay? So this kind of very simple means that given 2 sets A and B, we can systematically produce all possible elements for the Cartesian product. So each element, we consider the result of the Cartesian product is also a set, okay? So each element of the result will contain 2 parts. One part is element from set A, the other part is element from set B, okay? So here I think this kind of, I'm trying to use the video to represent how to perform Cartesian product in a systematical way. So assume here we have 2 sets, R and S. So the capital A just simply the attribute of R, and the capital X just the attribute of S, okay? So in this case, we can consider R and S also as 2 relations or 2 tables, but they happen to have only a single column. Understand? So a table can have multiple columns or can only have a single column, okay? So then given these 2 relations or 2 sets, how we perform Cartesian product, I think if you kind of know some kind of programming, I think we can do it in a very systematical way to produce all possible combined pair or ordered pair. So for example, we first pick the first element in R, okay? Then we combine A1 with every element in S, but one at a time, okay? So once we finish, then we move to the next element of R. Then we will repeat. Then we're going to take the second element or next element, and then combine that element with every single element in S, one at a time, okay? So we just keep repeating until we finish combining every element in R with every element in S. No? So in this case, since we have very small R, only contains 2 elements, so I think then we can perform this combination in the maybe in 2 rounds. So given R, this A is schema, attributes from R, and X is attributes from S. Then for the Cartesian product, we use R cross product S, okay? So that's symbol for the Cartesian product. Then the Cartesian product result will be a relation, okay, or a table, okay? So then for this new relation, Cartesian products result is schema. So basically, we simply combine the attributes of R with attribute of S. Then we come with the attributes of the Cartesian product. You know, it's very easy. Then how do we perform? So we take the first element of R, then we take the first element of S, then we combine the 2. since we haven't finished combining A1 with every single element of S, so then we still use A1, then we're going to combine with X2, okay? We got A1 is 2. Then we still use A1 because we still have X3 left in S. So we finish combining A1 and A3, X3. Now we finish combining with A1, combining A1 with every element in S. Then we move on to the next element of R, that will be A2. Then we repeat in the same process. We combine A2 with every single element of S. Now we finish combining all of them. So this kind of can be easily produced using the programming. Okay, so it's use loop. Okay, so that shows Cartesian product. Why Cartesian product is very important in the relational data model, because Cartesian product actually form foundation for the table drawing. So when we're trying to combine related records from different tables, then we're going to use Cartesian product. But we have to specify the conditions so that not every element in the Cartesian product result will be used. We only pick the records or elements in the Cartesian product that satisfy certain conditions. Those conditions usually will be specified as drawing condition. Okay? Okay, so let's look at a real-world example. Assume that we have two small tables: student contains student ID and the name, and also we have enrollment. So simply record who enroll which class. So we have student ID and we have class ID. Okay. So if we want to do the Cartesian product of these two small tables, we're going to repeat the same thing. So first we take the student schema and enrollment schema, then we combine them together, make the schema of the result, right? So SID, S name coming from student and the same number SID from enrollment. We just simply combine all attributes of these two tables together. Those attributes will be the schema of the new table. This new table basically the result used to hold the result of the Cartesian product. So we're going to follow the same idea. So we take the first element of student and then trying to combine it with every element in the enrollment table. Okay, so then since the enrollment table has two records, so we're going to combine the same first record of the student with the second record of enrollment. We got this one. Okay, now we finish combining the 111 Williams with every record in the enrollment. Then we move on to the next record in the student table. That will be 222 Johns. So we're going to do the same process to combine 222 Johns with every single record in the enrollment. Now if you look at the resulting table, the Cartesian product, so on the right we have the resulting table. So I do the color coding. So two records are representing red and two records are representing in blue. So what do you think? Those color coding means what? Do you have idea? No. Okay, so you see in the resulting table. So you can hear that each record in the resulting table actually contains two parts, right? One record from student and the one record from enrollment, right? So if you look at these two red records, so actually you can hear that the SID from student record and SID from enrollment record, they are matching, right? So what does that mean? That means that we really combine the Williams student information along with the course he's taking. You understand? Similar for the bottom one. So for the bottom one, we have 222 Johns, that's from the second record of student, and 2022, that's the second record of enrollment. But they happen to be the second record. But anyway, so the key thing here is that those two records, they have a matching SID. Okay, So that means that we combine the John's student information with the course he's taking, okay? But if you look at the middle two, they are in the blue color. And we actually, for example, the second record in the result table, we actually combine William's information with course that enrolled by John's. Okay, so it's okay for you to combine these two records together, but it won't tell you anything new. No, you understand me? Because why it's important? For example, if we look at these two tables, student table only contains student information, and enrollment table only contains enrollment information. So if we have a question that we want to list each student's name along with course number he's taking, okay? So then this question will not be answered by student table alone. Will not be answered by enrollment, because enrollment does have course number and SID, but not student name. You understand? So in order to answer this question, in practice, we have to combine these two tables together, okay? So that, for example, the two records in the red tells us not the name info, but also the course taken info. So in this case, given these two red records, we are able to list, for example, according to the question, ask for the name, list student's name along with course number, SIN number he's taking. Then these two red records give us that information, okay? But these two blue records will not give us that information because these two blue records pretty much combine a student information with another student's course taking information. So those two are not related. We combine them together, we will not get the right information we need. You understand me? So that's why this matching, so means that student record, the SID from a student record must match the SID from an enrollment record so that we can combine these two records together to get not only the enrollment information but also student information. You understand me? So this is basically in the SQL query means that we need to specify the join condition. So SQL query in the backend database engine, whenever we need to join the two tables or even more than two tables, and the Cartesian product will basically serve the foundation of combine the records together. But then we have to specify filter only the right records in the resulting table. So this filter basically means that we need to specify the conditions of the two records before we combine these two records together. We need to pretty much specify the conditions. The most of the time, the condition is that the two records have some matching columns value, okay? So then we can combine them. So this kind of Cartesian product, okay? Then the values in the tuple. So according to the relation data model, a tuple is a record, okay? So each record, if you imagine a table, a record in a table, each record may have multiple values or fields, right? So then each field or each value will be atomic. But atomic will mean that that value cannot be further divisible, okay? So this is also considered relational data model constraint, means that every attribute can only take atomic value. By atomic, we mean that an attribute cannot take multiple values. And also an attribute cannot take composite values. Okay, so that's basically means that atomic, okay? And then the next one is talking about relational model constraints. So there are several constraints for the relational data model, okay? One is called inherent model-based constraint, or sometimes called implicit constraint. So this constraint basically means inherent in the relational data model, such as in a relational data model, we do have that no duplicate tuples are allowed in the table. So that's called, basically that's the relational data model requirements inherent in that model specification. The second type is called schema-based constraints or explicit constraint. So those are the constraints can be expressed in the schema of the data model. So we're going to discuss this constraint more. And then the application-based or called semantic constraint or called business rules. So those constraints cannot be expressed in the schema of the data model, but they can be expressed and enforced by the application program. So one example of this data model might be if you're running on the online kind of retail store. So you may want to promote the sales of certain items. So if you check your inventory and realize that certain items, they're selling very slow, for example, then you want to try to promote the sales of those items, slow sold items. How we're going to do? One strategy is that depending on how much a customer buy or how much a customer spend on that item, you may give them like a certain amount of discount. Okay, for example, my daughter want me to order some some crazy candy called rock candy. I never tried that before. So we ordered it for her kind of New Year's gift. Okay, and then after New Year passed, then now the January is almost over. We still haven't got that candy yet. So then yesterday I received an email from that store asking me, we just realized that you haven't ordered our products for more than a month. We would like to give you some kind of 5% discount to attract me to order again. So I was so upset. I wrote them email said, okay, I still haven't got my first order yet. I'm supposed to get it for the New Year's gift, but now it's almost Valentine's Day. I haven't got it. So they suddenly realized their mistake. Oh no, we are so sorry. So they want to can offer me some kind of refunds. So I think this can be easily interpreted as a business rules. Means that if you really care to retain your customers, right? You want to give them the best service they can. Okay. If somehow maybe in the kind of holiday season you may have on one side you have your sales kind of skyrocketing, but the downside is that you don't have manpower to process those sales. So then you probably watch out between the users submit their order and your order has been shipped to them. If this time is too long, you voluntarily offer some kind of refund to their order. So in this case, I think at least you can suppress the anger, maybe still able to keep them in the future, So this can be a business rules you can implement in your database. You just simply check the time lapse between the order submit and the order shipped. If it's too long, you're going to just voluntarily to tell the customer you want to give them some refund. So this can be easily embedded in the database design and then to enforce. So that's called the business rules or application-based constraint, okay? So then for the relational database constraint, we mainly focus on the database schema-based constraint or called explicit constraint. So here it shows the common 5 constraints of the relational data model. The first one, the domain constraint. I think we discussed that already. So domain basically is identified by a name, data type, and the storage format for each individual attribute in a table or in a database. And the key constraint, we're going to discuss that. So key basically is considered as a single attribute or set of attributes that whose values is unique for every record in the table. Then we're going to study entity integrity constraint, referential integrity constraint, and also sometimes the constraints on nulls. Okay, so basically in your database design, you have a table, you may have some records you do not allow, some of the columns or attributes you do not allow the null values. I think in the class we discussed, for example, if I want to create a table to report all the students in my database class, okay? So I need to go to each one of you to try to record your name. So during my data collection process, I can enforce that no student record having the name field as null values, okay? Because if you have null values in the name field, you basically will not be able to identify a student. So here, I assume that I won't collect your sensitive information like your TIN number and your and your social security number. So what is a key? Key of a relation basically can be a single attribute or a set of attributes whose combined values are unique for every record in that table. So in this case, we can know that a key is defined on the table. Okay, so key basically, the attribute of a key basically coming from the same relation. So a key must satisfy uniqueness constraint and minimality constraint. So by uniqueness, we mean that no two tuples in that same table have the same key value. Okay, so key must be unique for every tuple or every record in the table. The minimality basically means that if we happen to have a composite key, we need to verify if it's a key. Okay, so we're going to examine if every attribute in that composite key is redundant, is needed or not. Okay, so this is called a minimum. So minimality basically means that a composite key must be minimal. By minimal means that all component attributes must be needed in order to satisfy the uniqueness constraint. Okay, so in other words, no redundant attributes are allowed. That's about key. Okay, so I think we also in the discussion about the assessment test. So we have the questions on both a key and a super key. Okay, so once again, a key, the definition on a key is more restricted. It requires that a key must be unique, a key must be minimal. Okay, so that's, you need to remember, these are two constraints on the key. They must be satisfied. Both must be satisfied. So in the assessment question, we also have a question about the super key. Okay, so super key can be viewed as a superset of a key. In other words, a super key must contain a key, and our super key can contain some other extra attributes besides the key. So that's called a super key. Okay. So once we have a key specified in a relation, then we also need to pick the one as a primary key. Okay. So if a relation schema has only one key, then that key will be also the primary key. You don't have any other options. But if a relation schema has more than one key, like 2 keys or 3 keys, then you have freedom to pick one of them and designate that one as the primary key. You understand me? So in this case, in the relation schema, you only underline the primary key. You don't need to underline the other keys. So you only need to underline the primary key. So if a relation schema has more than one key, then only one of them is picked as the primary key. Then the remaining keys are called secondary keys. So you really need to understand the relationship between the primary key and secondary key. So before the primary key is picked, there is no secondary keys. They all called candidate keys. Okay? So then you need to pick one candidate key as the primary key. So once primary key is selected, then the remaining keys will be called secondary keys. You understand? So that's why we have this candidate key. So candidate key, my understanding is that this key can be a candidate for the primary key. So you have maybe you have one-on-one candidate, then you only have to pick one of them. Okay? So let's see the example. Assume that we have student table. It has SSN, T number, F name, L name, gender, age, and a major. So this student relation has 2 candidate keys, SSN and T number. So each one of them is unique and can be used to uniquely identify a student. Do you understand? So if we know the SSN, then we know that that SSN can be only assigned to one person. So we know who that person is. If given the T number, we also know that a T number can be only assigned to one student. So we'll be able to kind of trace to which student is assigned to that T number. Okay, so that's why SSN is a key. T number is also a key. So we have 2 keys. So both SSN and the T number are called candidate keys. Okay, so then we have to select the primary key. So in this case, the SSN is selected as the primary key because it is underlined, no? So that means that T number is secondary key. Okay, so once you have more than one key, then you have freedom to pick whatever key you want to at the primary key. Okay, so there's no rule of thumb that which key is better than the other. But the people, I think, tend to pick the key with the minimum number of attributes, okay, as the primary key. Okay, questions? So then the key constraint is coming with relational data model. So it means that every tuple in the relation must have a unique key value. And no two tuples can have the same key value. So in this case, key is considered as identity information for each record in the table. Okay, so with the key, we are able to identify each individual record with no confusion. Okay. Then the superkey. A set of attributes contain the key is called a superkey. So short for the superset of key. So superkey must contain the key, and it also may contain some actual attributes. Okay, so that's why the superkey, since superkey contains the key, it also satisfies the uniqueness constraint. Okay, means that every record in the table will have a unique key, superkey value, because it has unique key value, so that it also has a unique superkey value. But a superkey may not need to satisfy the minimality constraint. In other words, superkey cannot does not need to be minimal. Superkey can contain some actual redundant attributes beside a key. Okay, so that's why the differences between the superkey and the key. Okay, so superkey can be redundant, so it means it can contain some redundant attributes, but the key cannot. Okay, so that's why the definition of the key is much stricter than the superkey. Okay, but a key satisfies the uniqueness constraint. So a key is also a superkey. A superkey might not be a key, depending on if the superkey does not contain any redundant attributes, a minimal, then the superkey is a key. Okay, perfect. Okay, so let's see some example here. So consider, okay, the car relation schema. So this is used to store the car information, contain the state, registration number. I think that's the means the state where the car is registered, registration number, VIN. So this VIN number is considered unique for every car, right? And the make, model, and the year. Okay. So assume that this car relation has two keys: state, registration number, and a VIN. So state registration number, so the key one is called composite key. By composite, we mean that the key contains more than one attribute. Okay. The key two is single attributes because it only has one attribute. So when you have a key contains only a single attribute, that key satisfies the minimality constraint. Okay. When you have a key like key one contains more than one attribute, then you have to make sure that both attributes are needed in order to satisfy the uniqueness. In other words, for the composite key, you have to make sure that a composite key satisfies the minimality constraint. Okay, a single attribute key by default satisfies the minimality constraint. It's minimal, but composite is not. So you have to make sure that composite is also minimal. So both keys are also superkeys, okay? Because superkey contains a key. So a key is also a superkey, okay? So in general, a key must be a superkey, okay? But a superkey might not be a key, depending on if a superkey is minimal, does not contain any redundant attribute, then that superkey is a key, okay? Questions? I know it's a little bit confusing, but I want to make sure that you understand everything. Good, so let's see some example. So give the schema student contains T number, name, major, degree. Assume that T number is unique for each student. So that means T number is a key, okay? Then it asks you to list some super keys. So first one, I think we list here all of them. So this pretty much all the possible super keys, because super key must contain a key. So here T number is unique, so that means T number is a key, okay? So then the super key can contain the key only. So in this case, the first one, T number is a key and also a super key. And also a super key can contain some redundant attributes. So we just simply group them by the number of the redundant attributes contained in the super key. So that's why we have T number name, T number major, T number degree. So these three are also super key, okay? And each super key contains a key plus one actual attribute. Then we come with another possibility of the constructor composer of the super key, means that a super key contains a key plus two more attributes, right? So that's why we have T number name major, T number name degree, T number major degree. Then we come with the last one, so T number with three attributes. So we have T number name major degree. So that's pretty much the last option, pretty much contains all attributes in the relation. Okay, so this shows the possible super key of that student relation given the T number as a key. Okay, so now let's go to another example. Given the schema student, we have same schema, T number name major degree. We have same assumption, T number is a key, is unique for every student. So which of the following is a key? So I'll give you kind of 1 minute, 2 minutes, go through these 8 options. So we have 8 options. So which one of them is a key? Okay, any idea? Any suggestion? How about the online student? Do you have any? So can you send me the list of the key? So we have 8 choices from 1 to 8. Do you have any idea which one is a key? Okay, recall that a key must satisfy 2 constraints: uniqueness and minimality, right? So then based on these 2 constraints, then which ones satisfy these 2 constraints? Only the T number, right? T number satisfy uniqueness, that's assumption, and also minimal, okay, because it's single attribute. Let's see how about the option number 2, T number the name.
Name can be same.
Name can be
Same.
So it satisfies uniqueness, right?
Yeah.
Does it satisfy minimal? Minimal means that we can remove one attribute, the remaining still a key. Okay. So right, so name is considered as extra. So means that option number 2 is not a key. It's a super key, but it's not a key because key must satisfy the minimum property. And this is not minimal because we can remove the name attribute, then the remaining T number still satisfy the uniqueness constraint. Understand? So in this case, means that when you really evaluate the key property, you want to make sure that uniqueness and most important minimality constraint. So it must be minimal. So in this case, number 2, T number name is not minimal, so it's not a key. Although it's unique for every record, but it's not minimal, okay? So similarly, it applies to number 3 and 4, okay? And number 5, 6, 7, 8. So it means that given these 8 possibilities, only the T number itself is a key. So only the option 1 is right. The remaining are not keys because they do not satisfy the minimum identity constraint. Means that it contains a key plus some actual attributes. So those kind of structure will not make them a key. You understand? Questions? Okay. So this kind of just shows that given once, for example, if you're the database designer, if you know you're more like a domain expert, you know the attributes meaning, you know the structure of the table, and you know the key, okay? So if a table contains more than one key, you only need to underline the primary key, okay? You pick the one as a primary key, you only need to underline that primary key. You don't need to underline all of the keys. You understand? So that's a requirement. Okay, now for the relational database schema. So I think we discussed relation schema, something like here, more like a table structure. You just give the relation name along with attributes, right? That's called the relation schema. The relation database contains multiple relations. Then the relation database schema is similar. So we use this capital S representing the relational database schema. So we have R1, R2, Rn. So each R1, R2, Rn representing a relation schema. Okay? So it means that a database schema is simply a collection of the relation schemas in that database. Okay? So let me see if they have, okay, so this is the relational database schema. So in this relational database, we have 6 relations or 6 tables, okay? So the database schema is simply list relation schema for each table, okay? Then for each table, we need to what? We need to underline the primary key for each table, okay? And there are some other notations we're going to discuss with you for the next class. So it's going to be the foreign key. So for the key, if a single attribute is underlined, that means that attribute is a key, okay? And in this example, we have employee department. They have single attribute as a key, but we have DPT underscore locations. So this schema has both attributes underlined. So that means that the both attributes together is a key, okay? So either one of them is not a key, the both together. So that's why the key, the primary key for the DPT locations is composite, means it contains more than one attribute. Once we have a composite key, that means that all attributes together form a key. Okay, each individual attribute of that key is not a key. Okay, so in this case, we have DPT locations. D number itself is not a key. D location itself is not a key. But if we combine the two together, means that the combined values of these two attributes will be a key, will be unique for our record in this table. Okay, so I think similarly we have worksum contains composite key, and dependent also contains composite key. Okay, questions? Okay, so I think we discussed pretty very important thing. So let me see. I think we probably can have 2 more slides to discuss, and we are done. So the entity integrity constraint. So this is another constraint. So we have a key constraint. That's for the relational data model we just discussed. Okay, the key satisfy uniqueness and minimality. Then the entity integrity constraint requires that primary key attributes of each relation cannot have null values. Okay, the reason is very clear. If you allow the null value, means that you don't have any value on the primary key field, then you no longer be able to uniquely identify each record. You can assume that if 2 records both have the null values on the primary key field, then you won't be able to distinguish them. Okay, because primary key values considered as identity, record identity for each record or tuple. So the entity integrity constraint requires that no null values in the primary key field. This is very simple. And the constraint are null, that means that some other constraints, even they are not at the primary key field, sometimes we may still require those fields cannot have null values. I think I gave you one example already. If I want to create a table for the students in this class, I will collect the name information, collect the major, then I think name field should not have a null values. Okay, so that's constraints on null. So that means that when you design the database, besides specify the primary key, for the remaining attributes, you still can specify some constraints on them. So not null is considered one of the constraints. You can specify on the attribute. And besides not null, you also have domain constraint, right? So can regulate what kind of values an attribute can take. Okay, so any questions? So if no, I want to stop here. So I think in the next class, we're going to study the referential integrity constraint. So this concept is a bit, I think, kind of is not as straightforward as others. So any questions? So I think we're going to spend maybe at least 2 more lectures on the relational data model. Then we are done with it, and we may have the first assignment. Okay. Okay. Any questions? If no, then we are done for today. Thank you. I hope to see you on Thursday.